So for our last segment here, I just want to look at two different decision problems on graphs that are both in NP, and only one of them is known to be in P. The other one is believed not to be in P. Okay, so here's the first problem. It's called the Eulerian circuit problem. So let's define Eulerian circuit, and then we can look at an instance of the problem and think about it. So the Eulerian circuit problem. All right, let me just define Eulerian circuit. So an Eulerian circuit is a closed path on a graph that visits each edge exactly once, or that uses each edge exactly once. So a closed path, closed means that it is a circuit, right? It comes back to where it started. So closed path on a graph containing every edge exactly one time. Every edge exactly once. So here's an example of an Eulerian circuit. So here's a graph. So there's a graph. This is a ridiculously simple Eulerian circuit. The Eulerian circuit would be to start here, go there, then there, then there, then there. Okay, that's an Eulerian circuit. Another graph that we could do that has an Eulerian circuit is we could just add some nodes to this graph. So I could say, here's another node, and we go there, there, and there. So what's the Eulerian circuit on this graph? Well, we can just augment the original one with a new one, right? It could be here, here, and here. Okay, so this is the blue curve here is an example of an Eulerian circuit. Now notice that the Eulerian circuit visits this node more than once, right? So an Eulerian circuit is only required to use each edge exactly once, but it's allowed to visit a node more than once. And so this node gets visited more than once in this Eulerian circuit, and that doesn't disqualify it from being an Eulerian circuit. Okay, so that's the definition of an Eulerian circuit. Now there's another kind of circuit on a graph that has kind of an almost dual definition. It's called a Hamiltonian circuit. So a Hamiltonian circuit is a closed path on a graph that visits each vertex exactly once. Okay, so the above, what I've written, is not a Hamiltonian circuit. It's an Eulerian circuit, but it's not a Hamiltonian circuit, right? These two definitions are not equivalent. So here it's a closed path on a graph visiting every vertex exactly once. So Eulerian circuit visits every edge exactly once. The Hamiltonian circuit visits every vertex exactly once. So here's an example now of a graph that has a Hamiltonian circuit that does not, but it does not have an Eulerian circuit. Okay, so here's an example of a graph on 4 nodes that does have a Hamiltonian circuit, and so here's the Hamiltonian circuit. Well, there's actually more than one, but here's one example of a Hamiltonian circuit. Goes like this. So now we've visited every vertex exactly once. We didn't visit every edge exactly once, but nonetheless. So I mean that means this is not an Eulerian circuit, but we visited every vertex, so that does have it is a Hamiltonian circuit. Okay, so we can convert each of these definitions of circuits into a decision problem. Okay, and the decision problem goes like this. So here's the I'm just going to call it the decision problem of each of these. Does a given graph have either of these circuits, right? So does a given graph have an Eulerian circuit? That's the Eulerian circuit problem. Or does a given graph have a Hamiltonian circuit? That's the Hamiltonian circuit problem. Does a given graph have an Eulerian circuit? And does it have a Hamiltonian circuit? Right? So these are two decision problems, right? So decision problems. Does a graph have one of these two circuits? So it turns out that there's a really fast algorithm for determining whether or not a graph has an Eulerian circuit. And there are also polynomial time algorithms for actually finding the circuit. But it turns out there's a trick with Eulerian circuits that we know of that allows us to very quickly determine if a graph has or does not have an Eulerian circuit. So here's our fact. A graph has an Eulerian circuit if and only if it is A, connected, and B, every node has an even degree. Okay, so what is the degree of a node? That's just the number of edges connecting to the node. So here's our fact. A graph has an Eulerian circuit, has an EC, an Eulerian circuit, if and only if, okay, IFF for if and only if, right? So this is a two-way implication. If and only if, one, it is connected. All right, and remember what connected means is that there is a path between every set of every pair of nodes. And two, every node or every vertex has an even degree. Has even degree. Okay, so I can ask you now, is this a polynomial time algorithm? Well, how would we check this? How would we check this? Well, one way you can check connectivity is you can do a DFS on the graph. So a DFS says I'm going to go visit every node and kind of build up a tree that tells me something about how I visited every node. And if that DFS, if the first pass of that DFS terminates before you visited every node, then you know it's not connected. Right? DFS is a linear time algorithm. All we have to do is process the input, and we don't have to do anything extra. It is linear in the size of the representation of the graph, right? So we can check connectivity in linear time. Okay, so this is linear time. Okay, and then we can check whether each vertex has an even degree in linear time as well, just by directly processing the representation of the graph. So if the graph is represented in an adjacency matrix, then we need to make sure that each row of the adjacency matrix has an even number of ones. Okay, and so that's one thing we can do, and that's all you have to do is one pass through the adjacency matrix and you're done. Or if it's adjacency lists, what do you have to do? Well, you have to go down the lists, and for each vertex in the graph, you have to make sure that it connects to an even number of vertices, right? So its adjacency list is an even length, right? Which again is just one pass through the adjacency lists. So that means this can be checked in linear time as well. Okay, so remember the decision problem here is, does a given graph have an Eulerian circuit? And what we've just illustrated is, using this property of Eulerian circuits, we can check whether or not it is a yes instance, a given graph is a yes instance of the Eulerian circuit problem in linear time, right? Quite fast, right? Linear in the size of the representation of the graph. So what is our fact then? Well, given the above characterization of Eulerian circuits in graphs, we can say that the Eulerian circuit problem, and I'll just write this out, Eulerian circuit problem is in class P. Okay. So this is certainly true. It's also clearly true and we can argue this for two reasons, but it's also clearly true that the Eulerian circuit problem is in class NP. So how do we know it's in class NP? excuse me. Well, there's two ways we can verify this. Well, for the first way is we can say, look, we know that it's in class P, and we have this Venn diagram. Every problem that's in class P is in class NP. So we're done, right? If you believe the Venn diagram, we're done. Alternatively, what we can do is we can say, hey, the Eulerian circuit problem is in class NP because if I give you an Eulerian circuit, or if I give you a closed path on the graph and say this is an Eulerian circuit, you can check to see if it's an Eulerian circuit in polynomial time, right? In fact, in linear time, in the size of the representation of that path. If it's an Eulerian circuit, then it's a yes instance. If it's not an Eulerian circuit, then I've lied to you about the proof, right? But yes instances can be verified in polynomial time. So it is in class P, also in class NP. Okay, now let's think about the Hamiltonian circuit problem. Okay, so here's a fact that I can say about the Hamiltonian circuit problem. So the Hamiltonian circuit problem is in class NP. How can I tell that it's in class NP? Well, for one of the same reasons I can tell the Eulerian circuit is in class NP. Suppose you have a graph, and I come to you and I say that graph has a Hamiltonian circuit, and you say, I don't believe you. And I say, sure it does, here's the Hamiltonian circuit. The question is, can you check to see if that thing that I gave you is actually a Hamiltonian circuit in polynomial time? And of course you can. You can in linear time. Because if I give you a closed path on a graph, to verify that that path is a Hamiltonian circuit, all you have to do is walk along that path, right, which takes linear time in the size of the representation of the path. So all you have to do is walk along that path and make sure that it visits every vertex exactly once, right? And then you're done, right? That's how you check. That's how you check if a given path is a Hamiltonian circuit. You just walk along and make sure that each vertex is visited once. And that it's a valid path in the graph, of course, right? So you have to double check it against the graph representation. But in any case, if I give you a path and I say this is a Hamiltonian circuit, you can check to see if it's a Hamiltonian circuit in linear, thus in polynomial time, right? And so let me just quickly write down why this is. So this is because a given path can be checked to be a Hamiltonian circuit in linear time. I'm going to say in polynomial time just so that we're connected well to the definition of NP. Okay, so these are two problems that look very, very similar. In fact, you can almost define them the same way by just switching a word, right? Switching edge for vertex. Both of them are clearly in class NP. Because if I give you the circuit, you can check to see if it satisfies the right properties quickly. However, the Hamiltonian circuit problem is very strongly believed not to be in class P. So the belief among theoretical computer scientists in general, the exact proportion of which ones believe this is debatable, but the generally accepted belief is that the Eulerian circuit problem is in P, right? So let's call this P. It's generally, it is known that Eulerian circuit is here. And it is believed that the Hamiltonian circuit problem is here. So what is this outer Venn diagram, or this outer set? This is the set NP, or the class NP. So it is believed that the Hamiltonian circuit problem does not exist in the class P. And the big question in theoretical computer science is whether or not it does, essentially. The big question can be boiled down to this. And we're going to get into all the guts of this in the next set of videos. But the big question, which is technically unresolved, is do there exist problems in NP that are not in P? And Hamiltonian circuit is one example of a problem that we think probably is in NP but not in P. Well, I should phrase that differently. We think it is probably not in P, even though it is in NP. But technically speaking, this question is unresolved. So the big question is, do there exist problems not in P that are in NP, right? So I've phrased this a little bit strangely, just to try to clarify kind of which pieces of the question are important. But here we have the Hamiltonian circuit problem. We know that it's in NP, and the question is it also in P, right? So another way to rephrase this question, it turns out, and we'll get into the details of this in the next set of videos, but another way to rephrase this question is Hamiltonian circuit is, and I'm just going to do this, Hamiltonian circuit problem is in NP. Is HC in P? And that ends up being a deep fundamental question in theoretical computer science. And we'll be getting into the guts of kind of what this question means in the next set of videos. But here's your introduction to it.